Alright, a bit of a shorter question this time. We want to sketch the graph of e to the sine squared x for 0 to 2 pi, and then we want to evaluate the integral containing this, and also cos cubed x and sine cubed x. While these two questions are fairly standard in what they offer, aside from probably the awkward functions, they have quite a nice link that you might find intuitive. And using this link allows us to get an answer much faster without getting bogged down in too much algebra. In order to get the intuition behind the shape of this graph, it's useful to know what a simpler version of this graph would look like. So we have e to the sine squared x, so instead let's just consider what sine x might look like. And we know that sine x goes from 1 to minus 1, and I'll put 0 here, and we go up, and then halfway, and then down, and then up again. So this is at pi, this is at 2 pi, and we can clearly see where the turning points are here. What happens when we square this function? So we have sine squared x. Well, I'll again put 1, minus 1, and 0 on. Note that if we square a number that has a modulus less than 1, it gets closer to 0, so it's going to get smaller. So it's more of a steep incline. And where we would normally drop below 0, we go up in the same fashion, as a negative number squared is positive. Again, this would be 2 pi, this would be pi, and 3 over 2 pi, and pi over 2. Note how the range has changed in both of these graphs. So we started off with it being in between the ranges of 1 and minus 1, and now we've got it in the ranges of 0 and 1. Now we can consider e to the sine squared x. What do we know about this? We can use the fact that e to the x is an increasing function. So, as you go to the right, it will always get bigger. So we know that the smallest value will be at the leftmost value. And here, well, sine squared x, we already know what the minimum value is. That's 0. And e to the 0 is just 1. Similarly, on the right side, the largest value is where sine squared x is 1. So we have e to the 1, or just e. This allows us to draw the graph, and I'm going to put 0 at the bottom here, where we have, so I'll put 1, and then e, so it's about 2.7 at the top here. And we start off at the bottom, we go up to e, we go back down, and then we repeat that, we go up to e, then we go back down. And this is the graph of e to the sine squared x. Another way we can approach the problem is by differentiating. Although you will have to use the chain rule and the product rule, we end up getting dy by dx is sine 2x of e to the sine squared x. And then we also note that this is 0, so it's a turning point, where this becomes a multiple of pi. So this gives us the solution 0, pi over 2, pi, and so on. So it's every multiple of pi. And we can see sort of how you might end up with this. So we'd have to differentiate again to work out whether the maximum or minimum point. And this can get quite messy. So it's definitely more intuitive to consider it by building up the functions from sine x to sine squared x to e to the sine squared x. We have our original function from part A, and we multiply it by cos cubed x times sine cubed x. And I feel like we can simplify this a bit. If we recall, we have that 2 cos x sine x is sine of 2x. And using that fact, how could we simplify this expression? Well, this is just cos x sine x cubed. And using the substitution here, we can get half sine 2x cubed. And making sure to cube the constant, we get 1 over 8, 0 to pi, times e to the sine squared x sine 2x. So we only have one function to deal with now. Wait a minute, what does sine 2x actually look like? If we draw a graph, so I'll put this at 0, 1, minus 1, you can see that it's going to be sine, but it repeats twice as frequently. So we have up, down, that's between 0 and 2 pi. So if we're only considering the first pi, we can consider everything to the left of this. And note that this is where pi over 2 is. And now, without any further calculation, we can work out what this integral on the left is. Note that the integral is defined as the signed area under the graph. And then, note that we're multiplying these two functions together. Furthermore, both of these functions are symmetrical in a certain way. Note that the area on the left here is equal to the area on the right here. And then, notice that the area on the left here is equal to minus the area on the right here. We can cancel out the positive and the negative areas to leave us with this integral is equal to 0. And this was mostly from just drawing graphs. We didn't need to do any fancy calculations or substitutions. We could just use the intuition behind how things worked in order to get the answer.